All right, well, welcome everyone. Okay, good. All right, so yeah, welcome. We're very glad to have you here tonight. I have kind of a smoky evening, maybe not as smoky as it has been, but yeah, great to have you. All right, hang on one second. Let me just check. Can you hear me? Trying to make sure our guests online can hear. Okay. Yeah, great. Welcome. My name is Brian Jackson. For those of you who don't know me, I'm a professor in the physics department here, teach physics and astronomy. You are joining us for our first Friday astronomy event. We're very glad to have you. For those of you who have never attended one of these events, these are a monthly lecture series. They take place on the first Friday of every month, 7 p.m. Mountain Time. We're in this room for now, probably for the foreseeable future. And so if it's the first Friday of the month and you're looking for something to do that night, you should be here because this is where it's happening. If you can't join us in person, you can also live stream these events. And we have QR codes out in the lobby there that can get you access to the YouTube live stream, which is actually running right now. And so you can watch this from the comfort of your own home if you can't join us in person. We actually have an archive of recorded talks going back, I think, 3 years now. So if you missed something, just go back on YouTube and check it out. We bring in a space scientist or someone who does space, kind of something adjacent to space science each month, usually from somewhere around the US. We've brought in, of course, astronomers, but also space policy experts, science journalists. So we do a variety of different kinds of lectures. And we have a great program coming up this next semester, of course, including tonight's lecture, but also on November 1st, we are very fortunate to be able to host Dr. John Mather. I think probably many of you already know this, but Dr. John Mather is the winner of the 2006 Nobel Prize in Physics. So he'll be here on November 1st. We're not going to actually be in this room. We're going to be over in the Student Union building in one of the larger lecture halls on the assumption that it's going to have a lot of people. So please join us for that. And for all the lectures this semester, it's going to be really great. After we do the lecture, we will usually do stargazing. Unfortunately, our observatory space is closed for repairs this fall. And so that stargazing will take place out on the quad this evening. We'll have some telescopes and things set up for you there. And we have begun, since the summer, we've begun doing stargazing every Friday night. So every Friday night after sunset, we'll be out in the quad, the grassy area here, if the weather's good, and we'll do stargazing. You can check the Boise State Observatory website. You can just Google Boise State Observatory. Our website will come up, and you'll see whether we're going to be able to observe that night or not by noon on that Friday. So check that page by noon, lunchtime on Friday, to see if we're going to observe, and we'll be out on the quad probably a lot this fall. These events, many of you will probably know, are completely donor supported. The costs for bringing our guests in, flying out to Boise, putting them up, feeding them, all of that, that's paid for by you all. And so if this is the kind of programming you'd like to see here in Boise, please consider donating. There's information out on the lobby about how to donate to our program. This is all thanks to you that these events are happening. And this is, I think, our 8th official year, completely donor supported. So it's been really great. You guys have been really big supporters. Okay, so excited to talk about tonight's presentation from Dr. Franck Marchis. Dr. Marchis is the director of the Citizen Science program at the SETI Institute in California. He is also the chief scientist for Unistellar, which I think we'll hear about a lot tonight. His expertise is in asteroids and astronomical instrumentation. We had a really great talk from him this afternoon, and I think you're going to hear a lot of the really great stuff that he talked about this afternoon, and maybe even some other stuff too. And so with that, let's welcome Dr. Franck Marchis.
Okay. Hi, good evening. Thank you, Brian. Thank you for inviting me too, by the way. That's my first stay in the wonderful state of Idaho. And I must say that I'm positively, amazingly surprised by the beauty of this state. I mean, the countryside is amazing. I traveled from Yellowstone to here. I stopped in plenty of places, and I hope I'm gonna come back. So if you want to invite me again, I will come back. Okay, so today I'm going to talk about astronomy, but specifically about citizen astronomy. It's not something very well known yet. So I'm going to explain to you first the motivation in doing this citizen astronomy, what we care about this. I'm going to start by something a bit more personal. You know, when you choose a job, you generally try to find a motivation, of course, for this job. When people ask me in an airplane, what do I do? I say, I'm an astronomer. Because I have a French accent, they generally don't understand me right away. But then I have to explain it again. As I look at the stars, say, oh, yeah, oh, you're an astronomer. Well, that's weird. You're the first astronomer I ever met. So, yeah. And then they want me to explain what I do. So I generally, depending of the type of person, I may say that I work at SETI. Most of the time, I don't say that I search for extraterrestrial intelligence. I just say I look at stars and I develop instruments. So one day we find life in our galaxy. That's truly the motivation, in fact. But this motivation comes also because I love the field of astronomy, because I always consider astronomy to be kind of the poetry of science. It's kind of the free spirit people in astronomy. If you look at astronomers, we always been the annoying people, the one who has been pushing the boundaries of human knowledge, the one who has been challenging the kings and emperors. Some of us did not end up very well. As you probably see here, this is Giordano Bruno, a famous priest and astronomer who wrote papers on the plurality of words and claim in the 16th, 17th century that there may be some alien civilization elsewhere in our universe. This didn't go well for him. He ended up being killed and burned. But yeah, that's the story of astronomers, right? We've always been pushing and pushing. But it's also a science which enlightened humanity. Most of you probably remember the first time you looked through a telescope. Who have seen here the ring of Saturn? You will always remember when you saw for the first time the ring of Saturn. That's something that will impacted you probably as a child, a teenager, or even a grown-up. So you remember where you were this time when you saw the ring of Saturn, the first eclipse, solar eclipse or lunar eclipse, because we are connecting to space. We basically, as human beings, love space because it gives us a sense, a purpose in life. We want to be able to answer to fundamental questions such as, are we alone? Why are we on this planet? How long our civilization will last? What is the future of Earth? And this is basically the question that astronomy will help you to answer if you have an interest in it. And that's one of the reasons I'm an astronomer, and that's one of the reasons we created the Unistellar Network, to bring astronomy back to the people. And I say back because we are entering in a very weird moment in life, in the life of our civilization, for which we can now fly in space, true. We can soon send hotels and people over there, but we're also losing our connection with space. And we're losing this because we are developing a technology that is blinding us. I call this the cosmic blindness. With all these lights of cities, most people can see stars. If you go to major cities like San Francisco, for instance, where there is no fog, of Los Angeles, you don't see more than 5 or 6 stars in the sky. I do remember as a kid growing up in the south of France, looking at the stars and seeing the Milky Way. And something which really surprised me when I ask young people today, most of them have never seen the Milky Way. Most of them don't even know what is the Milky Way. When they see the Milky Way in the sky, they're surprised. There is stories in Ukraine, for instance, because of the events happening over there. They have shortage of energy and no lights suddenly in major cities. And kids were very surprised to see the Milky Way for the first time. So this cosmic blindness makes us lose the connection with space. And I'm fundamentally believe that this connection in space is part of us being human. Connecting to space, connecting to our planet is part of us being human. So in short, that's one of the motivation of me being an astronomer and creating these telescopes called the unistellar telescopes. This is one of them. This is the Odyssey telescope. It's a digital telescope. It basically gets rid of this issue of cosmic blindness by allowing people anywhere they are, cities, suburbs, or the countryside, to be able to see and enjoy the beauty of the sky, see galaxies, nebulae, comets, and basically reconnect to space, looking up instead of looking down at social media or looking at Netflix every night. So we created these telescopes to get rid of this limitation of the cosmic blindness, the light pollution. A telescope which is easy to use. Anybody can use this telescope, even if you don't know anything about astronomy. You connect with a phone, and it will basically align itself and give you a list of targets. You can observe from your location. The challenge and the goal is that in 5 minutes, you should be able to observe a galaxy, a nebulae from your home. It's not a miracle. We're using technology that already existed at the time we developed this in 2019. Cameras get more sensitive, motors are better. So it's possible now to do this kind of telescopes. And it's been a very successful story, I will say, because in 2017, we did a Kickstarter. In 2019, we delivered the first telescopes, the Eviscope 1. And now we have more than 15,000 telescopes on the planet. And you see a map of them here. You see most of them are in United States, Europe, and Japan. We extended the network in Australia and New Zealand. And we're also starting having telescope in India and the Middle East. So we created this telescope for the image, but also for the science. And I can go through the detail of the technology later on if you have any questions, of course. So the goal is you have the telescope, you connect your app to the telescope, the telescope aligns itself, then it gives you a list of targets that you can observe. So let's say the moon in this case, and it will basically, point toward the moon, find the moon, center the moon in the field of view. You can see it on your phone or on the eyepiece in some cases. And then we have this magical button called Enhanced Vision, which is basically an algorithm that does astrophotography live for those who know about this technology. It's basically an image processing. And this image processing allows you to see the moon, for instance, in this case, with a better resolution. And you will see tonight, we're going to have a demonstration of this telescope and others, thanks to the student of the Boise State University. So this is the app. I'm going to show you that in person later on, so I'm going to skip this. And this is some of the observation we have taken from, this is the first observation with Eviscope 1 in 2019. So those are very old slides, but that's basically what you will see tonight if we have clear sky. The Whirlpool galaxy on the left, which is a galaxy relatively close to us, two of us, very close to each other. And the large one is absorbing the material of the small one. This is the Comet Atlas that we observed in 2020. And here you can see the Eagle Nebula, a nursery of stars. Here you're observing something which is thousands of light years away in our galaxy. And this, when you're looking at this, you are basically looking at a place where stars are being born. And the reason we have this colorful image is because we have very hot, energetic stars, which are emitting so much energy that they excite the environment around them. So the gas is excited. And what you see is the hydrogen emission line in this case. And if you look carefully, you may recognize something you have seen in the past on the internet. Those are the pillars of creation that has been observed and is one of the most charismatic observations of the Hubble Space Telescope. So these observations are taken from the suburb of San Francisco or San Francisco where I live. And that's really the goal here, is to bring the people to enjoy and reconnect to space, but also to stay with us by doing scientific investigations. And that's what I call the citizen science. So before going to the science, let me talk a bit about the big pictures here. We are not only developing telescopes, okay? We have done telescopes also for educations. There is a program here at Boise State, as you know, probably, They're going to deliver telescope in high schools. We have, with the funding of the Gordon and Betty Moore Foundation, we now donate telescopes in community college in the US, and we train the teachers so they learn how to use their telescope with their students. We have done an equivalent of what you're doing here in Boise State in California with what we call the Chabot Space Center in Oakland. The program is called Galaxy Explorer, sorry. And we have given 4 telescopes to this center, and they work with high school students in Oakland, in the area, and they have been doing observations. They observe exoplanets, and they, in fact, become co-author with my students, Daniel Peluso, of one of the confirmed exoplanets. So the goal here is to bring the young people to astronomy and scientific knowledge by making them do astronomy and connect them with space. We do outreach as well for people in general. So we bring telescopes as star parties. We have more organized events, such as in this case, an event we organized for the April 2024 solar eclipse. We have stations located along the path of the eclipse, sorry. And I was located in Austin here, and one of my colleagues was all the way to New York State. So we streamed the eclipse, and people couldn't really see the shadow of the moon passing above the surface of Earth. So the eclipse happening at different time with the locations. This is really something that I think is important for the young generation to be able to see and enjoy event like this, astronomical events, to be part of astronomical events like that. I mean, we have a lot of young people who were seeing for the first time an eclipse, and looking through a telescope, you see details and you have better understanding, of course, of what you're seeing. Like here we can see, for instance, the prominences of the sun at the bottom right. But we don't want our telescope to be only in the US or in Europe. We also want to have the telescope everywhere in the world. So we are partnered with the Astronomer Without Border and a group called Astro Sandbox to donate telescopes in various places in the world. The goal here is to expand the unistellar network, to expand our scientific connection of our scientific network, but also to connect this stargazer worldwide. To have people working together. They're coming from different countries, they speak different languages, but they are interested in one thing, it's astronomy, it's the link between each other. So here on the left, you have telescope we deliver in Ukraine, different colleges and university over there. Telescopes in Kosovo that's been used by this amateur astronomer club, and here telescope recently received in Brazil as well. And when I wake up in the morning, I can see how the telescope being used because we have access to this information. And it's always amazed me to see this tiny dot popping up in different places in the world. And I think that there is maybe an amateur astronomer club doing those observations and young people enjoying together observing the stars. So let's talk about the science. So Unistellar is a for-profit company located headquartered in Marseille with offices in San Francisco. But we have a partnership with the SETI Institute, the Search for Extraterrestrial Intelligence. And part of this partnership is to develop the science and education of Unistellar. We don't do that alone. We have been working with a lot of different institutions. See some of them. You may recognize some of them. We work with NASA TESS. That's the space mission that search for exoplanets. We've been working with different institutions around the world, Charles University in Prague, the AVSO, the American Amateur Astronomer Club for Variable Stars. Sorry, I forgot what it means. But we have been working with all this group. The goal here is to develop scientific activities using our telescopes and involving groups from different countries and different topics. We recently signed an agreement with the MSRO. You probably don't know what is MSRO. It's the Maldives Space Research Organization. It's the first space agency in the Maldives, country, as you probably know, south of India. And we signed recently an agreement with Alula Observatory, which is an observatory in Saudi Arabia. And always the goal is the same: develop scientific programs with those institutions. So I don't do that alone. There is a lot of people working on this project in the US, and I'm showing you here their faces because some of them may come one day or you may see them. So I'm the lead of this group of young, motivated, challenging at the same time, but also very fun group of researchers. Each of us work on different parts of the research. So Lawrence Grow, for instance, work on the exoplanet research with the Unistellar Network. Ariel works on comet activity. Ian Weaver works on outreach education, and Ryan on planetary defense, and Joseph in occultations. And of course, we have a mascot, my dog Stormy, that you may see tonight, by the way. She came all the way from San Francisco. So if you look at our website, you will see all the activity we have, okay? Every week, we change our website to put new comments, new activity, new scientific activity, new comets passing by, new asteroids flying by Earth, you name it. So we have this group of researchers working with this network of institutions, and we propose activities with our telescopes. And every morning, or when I can connect on the website and let's see who has been observing. So this is an observation last night, for the last 12 hours, basically, 24 hours. So you can see observation coming from Brazil, that was an occultation, and observation in the US, in Europe, in New Zealand, and in Japan. I can also see we have a complex pipeline that basically analyzes all the data received by these contributions. So you can receive an alert on your app telling you, hey, there is a new supernova, there is a new comet. You take your telescope out, you observe it, and then you send us the data. And we have a pipeline that analyzes continuously new data coming from the network and process them, identifying what is the type of observation and what kind of result, what kind of analysis we need to do. And you, as a user, you receive later on a report telling you how the observation was useful and what kind of observation, what kind of information we extracted from that. So this is really a new way of doing astronomy. That's something unique that's not been done so far. And the reason we had to do this is because we have more than 15,000 telescopes on this planet. So we're receiving a lot of data coming from all these telescopes. There is 2,500 registered and active citizen scientists in our network. So what do they do? Let's talk a bit more science. So we have one of the programs we started recently. One of them is called Transients. We started this in December of last year. The goal here is to look at the sky and see and then understand what are those events, this explosion of light that appear. They could be due to novae, supernovae, gamma ray burst. Generally, those are phase of evolution of stars or binary systems. We have surveys on our planet with ground-based telescope, extremely large generally, that can detect those events. Unfortunately, they see them and then they stop observing them. So what we have now implemented is a system for which you have an alert every time there is a detection of a bright flash of light in the sky. So you can be observing and you receive an alert on your phone saying, hey, there is a flash of light at this part of the sky. Do you want to observe it? You press yes, the telescope will go to this location, take the data and send it to our network. So some application is, of course, the observation of supernova. So you probably remember, if you follow the news of astronomy, of this supernova in the Pinwheel It's not the Pinwheel Galaxy, but M101. I forgot the real name. The supernova is called 2023 IXF. Not a pretty name, but it means that he was detected in 2023. And the story here is interesting because he was detected in this galaxy by an amateur astronomer in Japan. So you can see it here. That's an image before and after. That's a supernova, a flash of light, a dying stars, right? So here we enter this, basically what we're observing here is an explosion and the collapse of the core of a star. So this alert was sent to people in May 18, and we receive it. And the reason it was interesting is because this is a very close galaxy, only 10 million light years away from us, roughly. So we're talking about something which is in our neighborhood in terms of the size of the universe, of course. And so we send this alert to our network. And as you can see, for more than 35 days, we have multiple observations coming from our network. So tiny dots here. And this is what we call a Lie curve. So you have time on the x-axis and you have brightness on the y-axis, right? So the supernova exploded and become extremely bright. For those who understand, this basically increased by 6 magnitude. So it's a significant increase in brightness and then start stabilizing. So, and now fainted away. This is a very interesting result for us because we collected 252 observations. So every 3 hours, we have one data point coming from 100 roughly EV scope. And we published this because this is the most sample observation of a supernova ever taken. That means we have a point every 3 hours. And this is very interesting because you can see basically the profile of the supernova. And professional astronomers have been taking observation using the Hubble Space Telescope and other large telescopes of this supernova. But they can now see where the spectra was taken in the phase of evolution of the nova. So we published this, and what's important is that this and that's really the motto in our research is that when you observe, you become a co-author of the paper. So we have a paper with 123 citizen astronomers who basically help us writing the paper and are co-author of the research together with some professional astronomers. So we do also exoplanet transits. That's something always amazed me, and still when I talk about it and other people, is that with such a small telescopes, we can detect exoplanets. It's a lie. We don't detect the exoplanet. We detect the shadow of the exoplanet passing by in front of its host star. You probably know the first exoplanet confirmed was discovered in 1995, 51 Peg B, by what we call radial velocity. It's another technique where we detect the planets because of the motion of the planet on the star. In this case, we use transit. So we analyze the light of the stars, and when we see a small attenuation, we infer that this could be due to the fact that there is a planet, a host planet between Earth and the star. This technique has been used by spacecraft like Kepler and now by the TESS mission to find exoplanets. When you detect this as small attenuation of light, you have some information about the planet itself. You know roughly size, if you know the size of the star, and you know roughly its orbit. Unfortunately, TESS look at a part of the sky for 20 days roughly, and then move away and look at another part of the sky. And the pipeline analyze the data and then say, oh, there may be a planet in this part of the sky, but we need to confirm it. But TESS cannot point back to observe it again. So what the TESS team at NASA has been doing is to send what they call candidates, list of candidates or potential planet found by TESS. So what we do, our network, is to look again at these stars to see if we have a secondary occultation transit. And in this case, we confirm the existence of this exoplanet. It's not fancy. We wanted a pretty picture. You're not going to get a pretty picture. You're going to get another Lie curve, but that's what it looks like. So once again, this is the Lie curve, so it's time. okay? And this is the brightness. So what you can see here is that was before the transit, and then the transit started. So the star get dimmer slightly. In this case, I think it's less than 1%. And then when the transit, when the planet is going away from the star is becoming brighter again, and that's the egress. So with this kind of data point, and this coming from our telescope, that's on the left is the exoplanet WASP-50b, quite known. And on the right, we have the exoplanet TOI 2031.01. And I'm very sorry for the name, but that's the way we name planets, exoplanets. So the one on the right, I really like this because we were not involved. And that's what I like, in fact. What happened is that Bruno Guillet, living in Caen, in Normandy, in France, saw that there was this transiting exoplanets that he could potentially observe from his house. So what he did, he sent an alert to our network and asked for someone living in the US to observe, justice to observe this exoplanet later. So what you have here is basically the observation coming from France. So you see the beginning of the transit, and here the observation coming from Justice in Georgia. You see the end of the transit. And this confirmed the existence of this exoplanet. So once using a very simple instrument, these two amateur astronomers confirmed the existence of an exoplanet. To me, it's still extraordinary that we are now living in a world where we can detect exoplanets using small telescopes. It's still remarkable that we know that there is exoplanets everywhere in our galaxy. In average, there is 2 exoplanets per star in our galaxy. So when you look at the sky, remember, you're not looking at stars, you are looking at planetary systems. There is, around each of these stars, 2 planets in average in orbit around. This research, this result was published recently last month. It's not super fancy because I put this slide quite recently together, but it's the first confirmed exoplanet from our network. Basically, we had TESS send an alert saying, hey, we have this planet, the name is TIC 3938, whatever, you don't want to know the name exactly, but they estimated there will be a transit happening between a specific moment of time with an accuracy of 5 hours in this case. So we ask our network to do the observation. So multiple people observed these stars and detected the attenuation of light, confirming the existence of this exoplanet. And this is an interesting one because it's a warm Jupiter. So it's basically a planet like Jupiter, but located relatively close to its stars, not too close, but not too far, typically at 50 times the distance of Earth's sun, but also having an extremely eccentric orbit. We think that those planets are some kind of transition between a very distant planet in orbit around the star and a very close one. And this is it's something that has been confirmed using our telescope. So we have multiple observations like this of confirmed exoplanet with our unistellar network. So another project we do is to basically support NASA Planetary Defense Program. So you know that our planet is orbiting around the sun, but it's not alone. There is other planets, of course, but there is also a lot of asteroids. And some of them have this orbit that could cross our planet and basically impact our planet. We see that regularly. In fact, if you read the news yesterday, we have one of these asteroids, only a 1-meter size asteroid, that burned into the atmosphere above the Philippines. And the reason for which I'm talking about this one is because this one, we predicted it. It's one of the asteroids for which we saw before it happened that it will impact our planet. That's what we call the Planetary Defense Program, to observe asteroids regularly and making sure that they don't impact our planet. And if they do, to be at least able to tell when this will happen and what will be the impact. What will be the impact in terms of, will it burn in the atmosphere? Will it crash on our planet, destroying an entire city, or will it just explode in the atmosphere like the Chelyabinsk one in the year 2015? So with the Unistellar Network, we're helping NASA with this kind of with additional observation. We regularly observe near-Earth those asteroids, and we refine their orbit, and we also build the model, the shape of those asteroids. So when you observe an asteroid, it's not extremely exciting. It's not pretty picture. Once again, this is what you see. Let me show you here. You see a tiny dot moving with respect to the background stars. But because the tiny dot is an asteroid, which is not perfectly circular, it has an elongated shape, typically, and because it's spinning on itself, you can derive what we call the spin period of the asteroid. And from the spin period of the asteroid, you can also derive the shape as well from the amplitude. So this is some kind of work we have done over the past 3 years. We have derived the shape of multiple asteroids using several asteroids using this technique that was unknown. The period of an asteroid is important as well as its shape, because if the asteroid is for instance spherical and extremely compact, it will be different. It will have a different interior structures than an asteroid which is extremely elongated, for instance. So this is the shape of 1999 AP10. I'm sorry, once again, astronomers have zero imagination in naming things. So these asteroids, you see it on the left here, that's its tiny dot moving, right? On the right, you see the lie curve. Once again, time versus brightness. And these figures is not very fancy, but using mathematical models, we can derive the shape of the asteroid by combining multiple observations. So that's the first time we derive the shape of this asteroid. And the reason it's important is because it's a relatively large one. It's a 1 kilometer size asteroid. So this is the dangerous one. This is the one that we don't want to impact our planet, because they will destroy an entire continent. Multiple observers took this observe it in November, between October and November 2020, because that was the only time it was close enough to be observable using our telescope. Okay, so you remember probably September 26, 2022? That was a great moment in the history of humanity, in my mind, because that was the first time that we sent a spacecraft to impact directly an asteroid. That's the DART mission of NASA. And if you look at the news at the time, it was 2 a.m. in Europe, so it was probably in the evening in the United States. You may have seen that. This is basically photography, images captured by the spacecraft just before the impact, as it comes closer to the moon, Dimorphos or Didymos. You can see the surface of the asteroids, a rubble pie shape made of fragments with irregular shape. So this was great but the reason for which NASA destroyed a spacecraft is because NASA wanted to see is by impacting the spacecraft, impacting the asteroid, we could deflect its orbit, so slightly nudge it away. So making sure that we have basically the technology to move an asteroid, so learn how to deflect it to if for instance impact or it could be a potentially hazardous asteroid. So this impact happened in, as I say, in September, and it was visible only in the southern part of Africa. And we have telescopes in the southern part of Africa. We have some in Kenya. This is Susan Murabana. She did a star party during the impact, and everybody observed the impact live as it was happening in Kenya. We also have observers in Réunion Island. It's an island close to Madagascar, and they observe as well the impact. In fact, we did a live for those who really want to see. We have a live show on YouTube. But this is what they saw. with our telescope. I could make a noise here, but I'm not. So what you can see is the asteroid here moving with respect to stars, right? And the moment of the impact, you have this increase of brightness and then this puff, this formation of clouds of material around the asteroid. So this is a signature, basically, of the impact I've seen remotely from the ground using our telescope. Another Lie curve, because I love them. Time, brightness. This is before the impact. This is the time of the impact, the dashed line, and you can see an increase of brightness by 2 magnitude. So suddenly something happened and the asteroid became brighter. The asteroid became brighter because it was suddenly surrounded by fragments of gas, of dust and boulders. And from this Lie curve, and I'm skipping a lot of analysis here, we basically, Ariel Grekowski, work on this data and simulate the formation of a comet, because that's what we did. We created a comet, basically. And by using some modeling that assumed the size of the grains, the speed of this, knowing the speed of the spacecraft and so on, she derived the amount of energy that was transferred to the moon of Didymos. And she confirmed that with this impact, we deflected the orbit of the moon. So it basically slowed down by 30 minutes. That's this period of rotation around this. The period of rotation was something around an hour. The point here is not the number. The point is that we confirm with this tiny telescope and these 3 observers that humanity is now capable as a technology to nudge away an asteroid of 100 meters if it was potentially impacted our planet. So that we confirm that we have reached a level, a technological level, so we're capable of moving away an asteroid in space. And I think this is a great result for us humans and for our civilization, because there is a lot of those asteroids, 100 meter size, 100 meter diameter, that could impact our planet. We have seen a lot of them. We're talking about 10,000 of them, okay? So now we know that if we observe them regularly and we see that one may impact our planet, we will be able to deflect it by using the same technology. Call that kinetic impactor. So this is a result of a large collaboration around the world by people, citizen astronomers in our network. This is their location. And you can see this come from a lot of different countries in the world. But what really matters is that we publish this in Nature, which is one of the major journals in scientific literature. And they were all, once again, co-author of this paper. So we do comets as well. Comets are great, but they are so complicated. I mean, asteroids are amazing because they're not spherical, so we see variation of light because when they spin and so on. But comet is way more complicated. They're coming from the outer part of the solar system, most of them. So they're made of mixture of ice and rock. And when they come close to the sun, they have this kind of activity. So they basically sublimate. Okay, the ice, and it's not ice of water, it's ice of other type of molecules, CO2 and so on, sublimate, carrying with it dust, etc. They are beautiful. They form this kind of coma and then tail where they're closer to the sun. Unfortunately, their activity is extremely difficult to simulate. It's still something we don't really know how to do. So the best way to do that, to learn how to do this, is to observe them regularly and to get some kind of activity, to get some measurement of the activity of a lot of different comets. So we finally be able to classify them or refine our modeling so we see how they behave and we can anticipate what will happen, whether it be close to the sun or close to our planet. So we just started doing this. We have a network and with other large telescopes. But this is what the planet looks like. This is a comet C2022 E3, another crazy name. Huh? ZTF, discovered by a survey called ZTF in California. And this was observed by Scott Gardner, one of a citizen astronomer in January. So you can see the coma. You can see the tail. This is a tail of dust. And here you can see what we call the plasma tail. The plasma tail is a tail which is which is always radially opposite to the sun and is basically formed by ion which interact with the magnetic field of the sun. Without entering into the details, comets are like cats. They're unpredictable. They have tails, true, but then we don't really know how they're going to behave when they come close to the sun. We have some models, but they generally disappoint us. So these are other type of comets observed by Anushka Nardi. That's the comet Ponsbrook. If you read the news, this was a crazy comet because it keep having outbursts. So regularly, it became extremely bright and then fainted again, and then bright again, fainted again. He did that 7 times in the period last year when he came close to us. But it was a beautiful comet. Those are observations with our telescopes, and you can see some structures inside the coma. And those are what we call jets, basically. And due to the fact that the comet was probably irregular in shape, and when the heat of the sun was hitting the surface, we have this kind of pocket of gas that exploded, forming jets like this one. And that's the reason this comet was a crazy one. People call it the Devil comet because for a while it has this kind of 2 horns. But it was, anyway, we're still trying to understand how this comet works and what exactly happened. And then I'm going to tell you a bit about the future because that's what astronomers do, right? We like astrologer. We're going to tell you what's going to happen in the future. So this is a comet C2023A3, Chuchichan Atlas. Remember this name because you're going to hear about it maybe. So this was discovered in 2023. That's why it's called like that. And we have a lot of complication with this comet. It's like, I think we can write a book about it. So it was very faint, and then it's become extremely bright for some reasons, probably an outburst. And we asked our citizen astronomers to observe it. So this seems to be complicated. It's a bit complicated, but I want to give you a flavor of what we're doing here. Each point here is a name of an observer. Okay, so imagine the number of people who observed this comet since April 2023. We're more than 100 of them now. So we have some models. Ariel and the team of working on modeling this comet. And what we discover is that this comet is becoming fainter now. That's this data point you can see here. You see these are a collection of points, and it's getting fainter. Fainter compared to what we expected. So people started panicking because some famous astronomer started talking to the media in April 2023 saying, hey, this is going to be the comet of the year. And the press get excited about it. This is going to be the comet of the decade. You know how we are, right? So comet of the year become the comet of the decade. And probably in the next week, we're going to have someone writing a paper saying this is a comet of the century. Well, it's starting becoming fainter in April 2024. And people panicked because it was not behaving the way we expected. So some astronomers changed their mind and say, well, at the end, this is not going to be the comet of the decade, neither of the year. It's going to be very faint because of this behavior. It's disrupted. It's basically breaking up, and it's going to fizzle like it happens in the past. So Ariel did some modeling, and in fact, she has another crazy explanation here. What we're seeing here is a comet which is extremely dusty, and the modeling she has done is to introduce the presence of dust into the comet, more dust than gas, in fact. And what she's predicting is that because this comet is extremely dusty, we're going to have what we call a phase angle effect, which is the dust is going to behave like a perfect mirror for a very short period of time. And if she's right, in October, mid-October of so this year, in a few weeks, the comet will have a magnitude of -2. So it will be almost as bright as Sirius. It's going to be close to the sun. So in October, look at the sky, sunset, sunrise, wake up early. I think it's a sunrise. And look at the sunrise. You may see something extremely bright close to the sun, and that may be comet Chuchichan Atlas. So remember that if Ariel is right. If she's not right, well, once again, comet behave like cats. They do what they want. Okay, so I have 10 more minutes to talk about human things. Because you know, space is great. We're launching rockets now, right? We're launching space stations. This is an observation of the Falcon 9 from Vandenberg in California, observed with our telescope, by the way. I got almost arrested for this. So I'm just want to tell you the story. I went to a federal land. I didn't know it was a federal land, and it was a jail prison and a federal prison. And yeah, we got almost arrested for taking these observations. But anyway, we got that. It was fun. It was just to show that the telescope can also observe a rocket launch as well. But what really mattered to us is that now we can start observing things happening in the sky, like satellites. But in this case, we observe, for instance, the James Webb Space Telescope, the famous telescope of NASA, shortly after his launch, as he was drifting away and going to the Lagrange point. So you can see this tiny dot is a human telescope, which is going away of our planet. But we're launching more and more interesting thing in the sky. NASA launched recently the ACS-3, another cool name, right? It's a solar cell. It's a technology demonstrator. It's basically a cell, a CubeSat, a 12U. So it's not big, huh? It's like this, basically. And inside there is this membrane, which is folded, and it deploys membrane, which is now, I think, 9 or 6 meters in diameter. So this happened 2 days ago, 3 days ago. I went for vacation, so maybe it's a week ago. But anyway, quite recently. So we told that to our citizen astronomers, and in fact, we developed a tool to be able to observe those satellites as well. And this one is a very interesting one. NASA asked us specifically if we could try to observe it. And in fact, we detected it. So what you can see on the bottom left here is the first observation made by Marco Bilani. He's located in Vienna, Austria. And you can see the flash suddenly passing by. That's basically the ACS-3. On the left is before the opening. On the right is after the opening. And you can see a clear difference. On the left, it's very faint. On the right is extremely bright because after the opening, the surface, the membrane has been reflecting the light of the sun, and we can see it better. So last night, when I arrived in Boise for the first time, I took my telescope out and I say, hey, let's check. And I saw that ACS-3 was passing above Boise. And hopefully it's gonna work. If not, you're gonna have to believe me. Let's do it again. And I got it. So, and the good thing is that I point with my telescope, this telescope, toward the ACS-3 using our tools. I will show you if you want later how we can do. You can do that with our website. And I got it. And then I went close to my telescope and I look at the sky where the telescope was pointing, and I could see it passing in the sky. Because it's super bright. This magnitude right now, I think this one was magnitude 5 or 3 at the time I observed it. So if you want to see it, go on our website, science.unistellar.com, and look at, there is a specific section on satellite, and you get a map like this telling you whether or not you can observe it. And then you will also have a tool. You enter your location, and it will tell you where it's located in the sky and when it's passing above your house. It's a beautiful thing to see. To say that it's because it's slower than the International Space Station because it's further away. So what do we care about that, besides showing you that we can observe a satellite? Well, because in this case, NASA is testing a new technology. They're testing a technology that could be useful in the future. So the telescope, a satellite equipped with cells like that, can basically use the solar wind to move away, to move the spacecraft. So NASA is going to test this technology with the gigantic solar cell for the first time. And our telescopes will basically be able to confirm the observation, the motion of the solar cell from the ground. And that's the reason they ask our network to do those kind of observations. We will basically, from the ground, confirm that there is a motion of the satellite, or we will be able to see whether or not the solar cell works to move a satellite at different location around our planet. I think it's a beautiful technology. I mean, I like sailing, and this is sailing in space, basically. And he has been not testing that many times. I think there is like 4 solar cells that worked. And that's why I think this is cool that we can contribute to a test to validate a new technology that we may change the way we do space telescopes in the future. And maybe the way we explore space. Maybe one day we will send a solar cell like this to explore the moon of Jupiter, or to even go outside our solar system and visit Alpha Centauri. Just a diagram. This is not a diagram. It's not a lie curve. No, it's a year versus number of observation. What I want to show you with this figure is that our citizen science is not anecdotal, right? We are growing. Our network is taking more and more observation. We went from 1,000 observation in 2021 to more than 6,000, to more than 5,000 in 2023, and we expect to have more than 20,000 in 2024. We are really growing this network to the point that we are getting more observation that we can handle. So we have to be more imaginative, more creative to be able to analyze and to publish these observations. So if you are interested in joining the network, you can join by having a telescope, but you can also join by helping us developing the software of the future that will help us analyze this data continuously. So we are really entering in a very cool time for astronomy. I mean, you probably know that astronomy started with astrologer, right? Those were like scientists that were paid by kings, emperors to tell them the future. That was in the 1700s. Kepler was an astrologer. Tycho Brahe was an astrologer before being an astronomer. But of course, they were simply using the fact that they were astrologer to get the funding to do their research. In the 70s, we entered in a phase where we started exploring the solar system. That's the second revolution. The Viking mission on Mars are basically the beginning of this moment where humanity started exploring the solar system using robots. Now we are very used to the fact that we are sending spacecraft to Jupiter to explore the moon like Europa. We're going to launch the Clipper mission in October 9, to basically explore Europa and confirm the existence of ocean beneath the surface. The year 2000 is a very different year, a very different time for astronomy, because now we have confirmed the existence of exoplanets. As I mentioned, there is 2 exoplanets per star in average in our galaxy. That means there is 400 billion exoplanets, and statistical models from data collected by Space Telescope confirm that, imply that there is at least 300 million exoplanets like Earth, habitable, potentially habitable, temperate, and with the same size, plus or minus 10%. That's a lot of worlds. There are a lot of worlds where there could be life, of course. So we are entering in a phase where we're expanding what we call a new sphere, the sphere of knowledge of humanity. We went from Earth to the solar system to the galaxy, right? We cannot do this with only astronomers. The understanding of the universe will necessitate the contribution of people. We need millions of astronomers to basically understand the universe and to be able to protect our planets against asteroid impact, to detect the nova, and so on. So the idea of the unistellar network is really to create this network of millions of people that will be able to observe the sky and contribute significantly to our astronomical knowledge. I say unistellar, but there is other companies who are doing the digital telescopes. Okay, I'm not selling our product only here. It's becoming, digital astronomy is becoming a new way of doing astronomy, and citizen science will help understanding the universe. So I will finish by telling you that we are now in the process of developing our network in a lot of different directions. It's not a work I will do by myself. We have a team of people in Europe, in Marseille, working on developing the education program. We are looking for partners in museums, schools, colleges all around the world. We have, for instance, we are trying to grow our network in India at the moment. If you join our network, you will see that we are every week or every month, sorry, we are changing our app. We're improving it. We have implemented recently the transient events. We implemented the eclipse observation for the sun. We are going to do very soon the satellite constellation to be able to contribute to observation of satellites and so on. The goal of our project is to make science easier, of course, and more fun. Gamify. I hope that in the future we'll be able to get trophy if you observe 10, 20, 100 comets and you participate to the understanding of the cometary activity, for instance. So we are looking for partners, and if you're interested in being part of that, join us. We can join simply by following our social media, by following the SETI Institute. And I talk a lot about this telescope. I've told you it's amazing. So hopefully tonight we're going to be able to do some observations. Thank you very much.
All right, questions for Dr. Marchis? Questions? Yeah, right there. Be sure to repeat the questions here for us.
It was a large object impacting another large object. The large was not really. The asteroid is 120 meters in diameter, and the spacecraft is, I think, the size of this, basically, to give you an idea. But it was coming at 22 kilometers per second. And in fact, we have surprises. I didn't say that, but we were not expecting this flash and this excess and this formation of boulders and stuff around it. One person predicted that. Everybody else predicted that it will be barely visible. And in fact, the efficiency of the kinetic impactor is better than expected, because as soon the impact happened, the asteroid behaved like a rocket. It's starting ejecting material, and that's basically accelerated it as well. So there was two contributions: the push from the spacecraft plus the ejector of material. And that's the reason the kinetic impactor is a very promising technique to deflect an asteroid.
Next question. You're right there. And let me get you to repeat the question for folks.
Oh, sorry.
Yeah.
Do you have any dedicated groups of citizen astronomers who are going to be looking at T Coronae Borealis?
Did you repeat this one? Yeah.
Sure, yes, please.
So do we have anybody, any group of astronomers who are observing T Coronary Borealis, TCRB? Yes. It's in part of our transient program. I don't know if you can see much more here, but so this is a binary, this is a nova, which seems to be regular every 47 years or something like that, 80 years, yeah. So it's expecting to happen between April and October. So I don't know if I have the slides here. No, I don't, but I can show you if you want later. We have 10, 20 observations per night of this. It's like the target. People are observing it every time, especially it's observable at the beginning of the night. So we have a lot of observation. Everybody is hoping to be the first person to detect, of course, to win the lottery and to detect the explosion. So yeah, we have a program.
Other questions? Yeah, right there.
Thank you. Why haven't we discovered it?
What? Okay, wow. This is generally the other lecture I give. Why have we not detected life, discover life elsewhere? So, and I'm serious that I have two talks that I really give at the moment, is this one or why we have not detected life yet. There is a competition at the SETI Institute of 3 ways of detecting life. Okay, let me go through each of them. The first one is detecting life by detecting technosignatures. So assuming that the civilization is so advanced that it has reached the same level of technology or even better than ours. And this is using radar, radio antenna to listen to the cosmos, or looking at the sky to look for laser pulse coming from these civilizations. Jill Tarter, founder of SETI Institute, say, we just started the search. We have 200 billion stars in our galaxy, right? And last time I looked, we have listened in radio only 120 million stars. And only for a very short period of time, something like 2 hours for each. So she saying that there is no life in our galaxy is like saying, oh, I'm going in the middle of the ocean, I take a glass of water, I take some water from the ocean, I look and say there is no fish, so there is no life. We have not yet even scratching the surface of where is if there is life. The survey is very short, basically. We have not yet done enough in 40 years, but it's accelerating. We have candidates. I mentioned that to someone today. We have detected 8 radio signals that could be artificial coming from 5 planetary systems. But they did not repeat themselves. So that's why you just heard about it for 1 week and then that's all. They may repeat themselves in the future, and you will remember that I mentioned that to you. The second way is to look for life in the solar system. There is plenty of places where there is liquid water, and water basically was as soon as liquid water appears on our planet, life appears. So we think that liquid water is a key factor to have life like ours on a planet or on a moon. We have plenty of places in our solar system where there is liquid water, and Enceladus is one of them. When you analyze the geysers of Enceladus, you detect carbon, phosphate, sulfur, nitrogen, a lot of molecules that you see on Earth. And you also see complex molecules like CH4 and so on that indicate that there is a presence of complex chemistry in the bottom of Enceladus. But we have to go back over there and take a sample and analyze it to tell you, yes, there is life. So if you have $18 million and I put together a team of researchers, and we fly a spacecraft over there. We grab a piece of this material and we look for chirality, for instance. You know, life has been always chose a symmetry, and if we find chirality, prefer chirality in these complex amino acids, there is life. But we need $18 million, so any candidate. And then the third one is to search for life on exoplanets. So we discover 5,000 exoplanets. There is 5,000 candidate exoplanets, right? But as I mentioned, we don't see the planet. We see the shadow of the planet. if I see the shadow of this room, meaning the silhouette of everybody, and if you don't move, I will not know you're alive. So I will not know that there is life in this room, right? So it's a bit the same for exoplanets. So what I would like to be able to do is to see you, each of you. And that's what we do with adaptive optics system. We're trying to image exoplanets to be able to see the planet, to analyze the light of the planet, and see in the atmosphere whether or not there is signature for biology, or maybe signature of light coming from megacities. And that's something that we are working on at the SETI Institute. In fact, you probably heard about JWST has detected maybe the very weird molecules, dimethyl sulfide, which is a kind of molecules you see produced by plankton on the surface of ocean. But it's a very tentative detection. If that's confirmed, that means that there is life on this planet called K218b, another beautiful name. So we are going to find life in 10 to 15 years.
Well, it's 8:45, so what I'd like to do is to thank our speaker again.
Fine.
And then if you have additional questions, I'm sure he'd be happy to stick around and answer your questions. We have some telescopes set out on the quad. Just turn to the left as you exit the building here. And you're welcome to stick around and stargaze with us. Have a good weekend, and we'll see you in a month.
Thank you.